This first unit is really a big one, right? What I may end up doing, we'll see. Like I might just break this up into like two parts of a test, so it's easier to retake. Possibly, we'll see kind of when we get there. They're not after this first unit. The units are more breakable. I mean, right now though, it's hard to break this thing up into pieces because it just all goes together so much. So this first one is exceptionally large unit. They will get smaller after the first one. Okay, so we got a couple. I want to wrap up talking about end behavior. Okay, so we're looking at some asymptote stuff here, right? Think what we talked about yesterday. We're developing techniques for determining what the vertical asymptotes of a function are and what the horizontal or slant asymptotes are, if they exist, right? You can't have both. You either have a horizontal asymptote or a slant asymptote, right? Makes sense you can't have them both, right? Because functions can't overlap vertically. So how could you have a function that is as it goes to infinity is adhering to two different asymptotes? That wouldn't work. That would mean that we'd have to have functions that overlap vertically and would violate the vertical line test. So those are kind of an either or thing, right? So here's where we left off. So we want to compare this power function model to its polynomial model. And you guys were doing this one on the board, right? What did you get? Some people did it correctly. So just tell me, like, what did you get for your answer? When we simplified this, you got f of x equals what? Do you remember? Someone took a picture, right?
Well, but we had the wrong one because we had the x to the third.
Did you guys have? Yeah, and that's fine. We'll do the x to the third. We'll just do x to the third. Yeah. 3x squared plus 6x plus 2, and there was no remainder, or was there a remainder? Okay, so there's our function. So then what would the polynomial end behavior be of this thing? What's the polynomial end behavior? Okay, but which part of the function? So if I wanted to define, let's define some polynomial p of x that predicts the end behavior. Which part of that is the polynomial part? First part, right? The part excluding the rational function, okay? So this is the polynomial part, just that stuff. Okay, so what I decided to do here, I'm just going to show you, let's look at these graphs and see if we can kind of see what's going on. This is worth inspecting and checking out here. So what do we get? I've got to go into Desmos and build this one. I guess it's not built, my bad. Oh, there we go. I did have it built, nice. Okay, so there's our function. There's f of x. Okay, what if we look at just the power function that predicts end behavior? I mean, it's pretty good, right? If we zoom out, we can see that it is going to eventually have the same type of end behavior, but it doesn't stick to that function great, does it? Let's stretch out the x-axis a little bit. How about negative 10 to 10? Right, we can see that it's kind of, it's shifted a little bit from the function. Tells us what kinds of infinities it's approaching, but beyond that, it's not great fit. Check out the polynomial on the other hand. Wow. Okay, that's pretty good, right? The polynomial that predicts the end behavior is very good. I mean, it matches that thing very tightly. Yes, sir.
Is that still considered a science?
Okay, no, it's not. An asymptote is linear. So this is an envelope, is what you'd call this. This is telling us, like, if we wanted to look at the end behavior of this thing, it's a parabolic envelope. So those are not as easy. I mean, they're harder to graph than asymptotes, and so we don't usually talk about that, right? We just graph the function. But if we were to graph that green function, you would get the end behavior, accurate end behavior of that function. Just everything in here where we have small values of x, it would deviate pretty wildly from that, right? This is purely just for predicting end behavior. Okay. But I guess the moral of the story here is just that the power function is nowhere near as good as the polynomial model, right? The polynomial model, when we're trying to simplify a rational function, way, way better. Okay, and we've been using that to our advantage. So what about something like this then? So let's just kind of go through a few quick examples. What are the equations of the vertical asymptotes, if any exist, and the horizontal or slant asymptotes, again, if any exist? So what are we going to do here? Okay. In fact, what am I probably going to want to do to both the numerator and denominator of this rational function? Factor them, right? I'm going to factor them because I want to know what the zeros are of the denominator, and if those are mirrored in the numerator. If they're unique zeros of the denominator, then they're vertical asymptotes, right? Uh, that's a good habit to get in because and in the future, we're going to do a lot more than just find asymptotes. And almost always, the first thing we're going to do when we have a function, if we're trying to look at like anything that's non-calculus, asymptotes, zeros, x and y intercepts, we're just factoring the top and the bottom, right? So what does the top factor into? What are the magic numbers here? Are there any? Okay, there aren't any, are there? Okay. So the top doesn't factor. How about the bottom? 2 squared. Okay, if the top doesn't factor, then we know. I mean, like we can just leave the top as it was. It didn't factor, so is 2 a 0 of the top? No, it's not, right? Because that would have factored then, right? And we can just plug it in. If I plug in 2, I'm getting 4 plus 6 minus 15. Clearly not 0, right? So what do we know here then? We have unique zeros of the denominator at 2. What does that tell us? Vertical asymptote, right? Okay, so because we have a vertical asymptote at x equals 2, right? Okay, give me 1 to 5 on that. Is that all making sense? Good with that? Okay. All right, horizontal or slant asymptotes. You can tell me right away what's going to be our horizontal asymptote. It's going to be 1, isn't it? What's our rule? Okay, so no, how come it's going to be? We are going to have a horizontal asymptote at 1. Okay, good. We have the same order of or same degree of polynomials on the top and bottom, right? So we do the ratio of the leading coefficients. Is that what you were trying to say?
I was gonna say all three of them, but
Oh, okay. Okay, so the other way we could do that one is we could just say the limit of g of x as x approaches the infinities is equal to the limit of the ratio of the leading terms, which is equal to 1, right? Either way. Either way you slice it, we get 1. And so we end up with a horizontal asymptote at y equals 1. That's supposed to be an add. Okay, good? All right. How about that guy? Any vertical asymptotes? Negative 18. Clearly that's going to be a 0 of the bottom only, isn't it? Right? Okay, so good. We get vertical asymptote at x equals negative 18. Good. And are we going to get a horizontal asymptote here? No, we're not. Good, because the top is higher degree than the bottom, right? Okay, but what do we see about this? We talked about yesterday that might be useful. What's important about the degrees of those polynomials? Okay, good. So the degree of the numerator is exactly 1 greater than the degree of the denominator, right? So when I simplify that quotient, I'm guaranteed to get a line plus possibly some remainder part also, right, which we'll ignore. So if we divide this out, which we can do synthetically, fortunately, what do we get? Okay, so if we make a synthetic bracket, what are the coefficients that go in the top row? Okay, got to remember to put my remainder box. What number goes out front? Negative 18. Okay, so we'll run through this process and we get, drop the 1 down, right? Negative 18. What goes here? Negative 34. And what goes here? Who cares, right? I'm going to get some number, and we don't even really care. It's going to be some huge number. I'm going to get some number there, which is just going to be my remainder. Okay, we don't really care about that if we're trying to come up with a slant asymptote. We don't care about the remainder part. We just care about the polynomial part, the linear polynomial part of that quotient. So f of x then, we could break it into 2 parts. What's the polynomial part going to be? X minus 34 plus the remainder is, who knows, right? Some number. We don't care. Who cares over what? X plus 18. But we don't really, I mean, we don't need that part, do we? We just need the linear part, which gives us the equation of our slant asymptote, right? So we end up getting a slant asymptote at y equals, right? Y equals x minus 34. Good? Okay, good. We got a vertical asymptote and a slant asymptote. That's good. That's going to make this thing easy to graph eventually. Okay? Questions? Good. Okay, let's look at one more, little tougher one. Okay, very similar problem. Are there any vertical asymptotes, first of all? Right, how come? How about vertical asymptotes, though? Okay, good, because look at the denominator. Are there any zeros of any real zeros of the denominator? No, right? If we try to find, if we look for real zeros of the denominator, x to the 6th plus 1 equals 0 nowhere, right? If I try to solve that, I get x to the 6th, and even power of x equals a negative number, which we can't do with real numbers, right? So therefore, there are no vertical asymptotes. Are there any horizontal asymptotes? We already answered that. No, how come? Greater power on the top than the bottom. Good. Okay, but what's important about the degrees? One more. So do we have a slant asymptote? Yes, we do, right? Okay, what's really kind of a bummer about this one?
Can't do synthetic.
Yeah, I don't have a linear denominator, right? So I've got to long division. I got to divide this thing out, right? Which is no fun, but we probably, how many people feel like they could use just a little reminder how to do long division? Okay, let's go through this one. All right, so we're going to divide this out. What goes inside the division bracket? Numerator. Okay, what's important about the way I write that out? Good. I have to carve out a column for every power of x. Very good, right? Because we're going to be doing a lot of subtracting of terms. We want to be able to line up the terms, the corresponding powers of x. I want to line them up with every step. So we have to make sure we've got columns for each power of x. This is kind of a pain, but we've got x to the 7th plus 2x to the 6th plus 0x to the 5th plus 0x to the 4th plus 0x cubed plus x squared plus 0x plus 2. Oh, I just made it. Okay. Out front, what goes out front? Denominator. I don't have to, I can just leave the denominator compacted. I can have zero, I don't need to write zero coefficients. So x to the 6th plus 1. All right. So now long division. What do I do? Exactly, right. So we want to divide the leading term outside into the leading term inside, right? So in this case, and we can always just write it this way. We can write it as x to the 7th over x to the 6th gives us what? X, okay? So this one isn't going to be so bad because we're already down to the linear term, x to the first power. So we're not going to have to do too many iterations of this. Okay, what's next? Okay, good. I got to distribute it and then subtract, right? So we'll go take this guy and distribute it to both parts, and that's going to give us x to the 7th plus x. So I got to put the plus x clear down there, right? Okay, now what did I always harp on when the next step? Tabor's got this. Okay, fill it in with powers. But remember, I always said you were going to put this in parentheses or brackets and put a negative sign out front. Remember that? That way you always know you're going to make triangles when you subtract. This term minus this term. It reminds you you're subtracting every time. If you don't do that, if you don't put it in parentheses, people have a tendency to forget, okay, did I distribute something or did I, this way you know you never distribute. The negative is always out front. So those guys cancel, as they should. I would just bring this guy down because I'm subtracting 0. So 2x to the 6th plus 0x to the 5th plus 0x to the 4th plus 0 cubed plus x squared. 0x minus x is what? Negative x. So minus x plus 2. Okay, now what? Do it again. Okay, so now we've got 2x to the 6th divided by x to the 6th is what? 2. Okay. So our next term is plus 2. We distribute again, right? And that's going to give us 2x to the 6th plus 2. Put parentheses around the whole thing and subtract. And what do we get? Those guys cancel. That's a 0, so we can ignore it. That's a 0. That's a 0. We're going to get an x squared minus x. And that's it, right? So that's our remainder. How come? Because x to the 6th won't divide into x squared anymore, right? If I were to try to do the next step, I would end up with an x squared divided by an x to the 6th, where the bottom is a higher degree than the top, and so we know that's not going to work. Okay, so then what does this simplify to? What's the polynomial part of my answer? X plus 2, which is linear, plus what's going to remain over my denominator of x to the 6th plus 1? X squared minus x. Good. Okay, and so just to remind us from yesterday, we kind of glossed over this in the last example, but then really what we're doing when we're finding slant asymptotes, we are still just taking limits at infinity, right? So we're doing the limit of f of x, we'll just call it f of x, as x approaches the infinities is equal to the limit of that, right? We simplified the quotient and we get the limit of x plus 2 plus, oh my goodness, come on, there. Okay, what's going to happen to that limit? What happens to that limit? Anything go to 0? Yeah, the remainder term, right? That rational function will always go to 0. And so we just get the slant asymptote, right? So our limit is then equal to the limit of x plus 2. So we get a slant asymptote at y equals x plus 2. Okay? And I see if I have this thing graphed. We can look at it. It's always kind of fun to see what we did. Oh, I guess I didn't. Okay, let's graph it real quick just to see it. Okay, so our original function this time was x to the 7th. Plus 2x to the 6th plus x squared plus 2 divided by x to the 6th plus 1. Okay, so if we graph that, there it is, right? Looks something like that. Kind of weird looking, okay? Does that look like it might have a slant asymptote? Does to me. Does to me. And our slant asymptote, what was it again? It was x plus 2. And look at that. How about that? Great fit. Okay, the slant asymptote. When you have big powers of x like that, it usually doesn't take long for that slant asymptote, for the thing to snap onto the slant asymptote like this one did. Okay, good. Any questions? Okay, that's kind of nice. So that ends everything related to, you guys saw the assignments I put up? Okay, so that's everything related to those is done. Okay, we'll talk about sleep a little bit.